In this video, I will talk about restoring force or restoring torque in studying physical oscillations. The first example here is a spring attached to a mass, and the spring has spring constant K. The mass here is M, and when we stretch the mass to a new position, L naught here is the original length of the spring. Now we stretch it by an additional length delta L. Then according to Hooke's law, we know that a spring force, F spring, is generated in a spring and applied on this mass. And its magnitude is given by the spring constant K multiply the additional length delta L. Okay, so that gives us this spring force. And such a spring force is always opposite to the displacement of the object. For example, right now the object is on the right side of this position, and this position also has a name. It's called the equilibrium position. It's to the right side of the equilibrium position. And the spring force is pointing toward the equilibrium position, okay, and to the left. So F spring, we know force is vector, and the displacement delta L, which is also a vector. So let me draw this delta L. Okay, so now we regard this one as a vector. These two vectors have opposite directions. So let's put the next sign here to represent these two vectors pointing at different directions, opposite directions. Okay, so one thing we can summarize here is that the spring force is always opposite to the displacement of the object. And the spring force, or the restoring force, always point toward the equilibrium position. Another example here would be when this mass arrives at the equilibrium position, but it will not stop here, because right now it's going to have some velocity, and it's going to keep going to the left side until a maximum compression, probably here, is symmetric with respect to the equilibrium position. And in that case, now the displacement for the object is delta L, and this delta L is to the left side, And the spring force now is going to push this mass M toward the equilibrium position. And that direction is again pointing toward equilibrium position. Okay, so that's restoring force for a spring system that is doing oscillation. Now, how about other cases of oscillation? This example here is a rigid body, a solid disk, let's say. Solid disk, and it has mass M and radius R. Now, going through the center of this disk, there's a metal wire. And it's fixed on the disk, right at the center. And if we twist this disk by some angle, as shown in this picture, by angle theta, twist it by angle theta, and then let go, then this solid disk will vibrate or oscillate back and forth, right, between these two positions. That's angle theta, maximum position of right side twist, and it's going to oscillate to the left side, also angle theta with respect to this center position. And that, with respect to this position, and that is the equilibrium position. So with respect to that, we're going to have this kind of oscillation back and forth by angle theta. But now, why we have such an oscillation? We know in order to have rotation, there need to be torque applied on such an object. And the torque comes from this metal wire. So if you twist this metal wire, it's going to generate a restoring torque. And it's given by kappa, which again, just like K in a spring constant case, kappa is a constant and it's determined by this metal wire's material. If you have different metal wire, then there will be different kappa for such a twist, and multiply theta here. So it's also a linear relation. The torque is proportional to angle theta that is twisted. Okay, just like in the Hooke's law. This is Hooke's law for rotation. Okay, and we know this torque is going to try to restore the disk to the original position. So the torque should point in opposite direction to the angle theta. So that's why we also have a negative sign here to represent these two vectors directions, the relation between these two vectors directions. Okay. All right, so that's the concept about restoring force and restoring torque.